Hello everyone and welcome to this new video. This is the third and the last video regarding the sequence to sequence. Remember that in the first video we saw the theoretical part, then the math part, and now we're going to see a pet project just to practice what we learned, and so we can move on with the other subjects. Okay, let's see the project overview. In this project, we will explore the capabilities of an RNN by training the model to perform simple arithmetic, so addition. However, we will not teach the model any of the math rules, like what to do. For example, carrying over digits in the, like for example, 12 plus 8 is 0 and you get 1, so on. But instead we will treat addition as purely sequence to sequence translation task. So we're going to change them into strings, similar to translating English to French or any other translation. This is not an RNN, sorry, this is the LSTM. We're going to be using the long short-term memory. So what we will do, we will build the entire pipeline from scratch using PyTorch. We will create synthetic or fake data where we will generate 55,000 random addition equations, input of a plus b and the target. Let's see an example. So this is an example of our fake data. This is one row. We will generate, for example, 1 and 1. The addition equals to 2. So, and then, so the first row would be, we will change this into the input, and this is the target, but as strings. So we will have 1 plus 1, not as an equation, but as a string. Imagine this is a data frame or a table. This is the input row, and this is the column, sorry, and the target would be 2 as a string again, not as calculation. Then we will implement the trick in the Google paper by reversing the input string to improve optimization and tokenization into characters into tensors. We also saw this in the previous video. So this would be, let's say 1 plus 2 is 3. So it would be 3 plus 1, 2 plus 1, sorry, is 3. Of course, all are strings. Or as another example, 10 plus 22 is 23. So it would be actually 22 plus 0, 1, not 10, because it would be reversed. And this one should be 2, 3. Again, it's reversed. This is just to get this value close to this value. So 2 is very close to 1. 2 is very close to 1. So for the model architecture, we will construct an encoder-decoder LSTM, which is the standard architecture for these tasks. For the training, we'll use teacher forcing, as we said that it would force the next input in the LSTM to be the correct answer. And then we'll build the autoregressive loop and let the user to interact with the model. So what should we expect? The model should accurately add the numbers that it has never seen before. And it should demonstrate that neural networks can approximate complex rules like the addition logic just by seeing enough examples. Here, since we are using math as a language or strings, it should fail if we do, for example, subtraction like 10 minus 5, because it didn't see minus in its training phase. We can see the architecture that we're going to use. As we said, the encoder part would give us the context vector, and then we start by the start of sentence token, and that would predict until we reach the end of sentence token, and we will use the teacher forcing rule, where at each step, even if it predicted the wrong value, we will force it to use the correct one in the next LSTM cell, and then it would the output should go into the linear or dense layer using the softmax function until we get the output. So this is, as we said, it's reversed, so it's 13 plus 5, which that should be equal to 18. Okay, let's start. Make sure we're connected to the collab. Okay, the first thing is we run these libraries, and then we will make sure we're using the GPU. Okay, we will also see it here, the GPU, so it's redundant. Now we will set the hyperparameters, batch size, learning rate, the epochs, the embedding dimensions, the hidden dimensions like the size of LSTM hidden and cell states. In this case, we use 256. The max length input. So we would also always add empty characters if it's less than this maximum 8. So for example, 999 plus 999, these are 7 characters. So we will add one empty space. And then the max length target should be maximum of 5. Again, we will add an empty character. So for the vocabulary, we will add from 0 to 9 and the plus. We said only additions. So and then for the vocab, we will sort the list of characters plus the special tokens of SOS and EOS. Then character to index, where the dictionary mapping characters to integer indices for embedding lookup, etc. Compose the video and read all of these. So the vocabulary is this empty character plus 0 to 9 SOS and EOS. This is, as we said, redundant. You can remove it. Okay, so we will generate the data that we talked about from 1 to 999, A plus B, and then make them all like strings, the input and the target. We would do like 50,000 samples for the training and 5,000 for the validation or the testing. Here we set the seed. I don't know if we did. Okay, we did not. So every time we will generate new data. Okay. And now for the pre-processing, we will convert the raw strings into tokenized tensors and create the PyTorch data loader. We will do the reverse trick, the tokenization, padding, as we said, like 7 becomes 8, 6 becomes 8 for the input. Target pre-processing, again, append token to mark sequence and pad with the tokens. And we will move them all to the GPU for faster computing. And we would set the batch size is 128 to group each 128 sample per batch and make the shuffle true. This is the code. We run it. And now for the model architecture that we just talked about. And so in the image, we will have the output 14, dimension of embedded vectors 128, hidden dimensions 256. These are for the input. This is for the output. For the teacher forcing ratio, 50% of the time we would use the the truthful or correct token. So not 100% of the time. And then for pass logic, we will encode the process reversed input, decode initialized with token, loop, force to use the teacher forcing, and return the prediction for all of the time steps. Now we will initialize the model using these hyperparameters that we used. Okay, now for the training configuration, we will use a learning rate of 0.001. We can go even lower for slower, but at the end more stable learning rate, not learning rate, but loss rate. We'll use cross entropy loss for the loss function, and we move everything to the device, in our case GPU, etc. We in this example we'll use 50 epochs, and then later we will I will come back to this section and make it like a very small number, like to show you how the model can fail with very small or short training phase. So let's run this. Since it's in the GPU, it shouldn't take a long time, especially in this very simple example. So after a few minutes, we can see at each epoch the loss is decreasing. This is not actually 0, it's like 0.00000 something. We have numbers, just in the output I've only shown like the 4 decimal points. So okay, it's finished. So this is very small value, but it's not actually 0. Okay, so for the evaluation or the inference, the first thing we do in PyTorch, of course, is to switch the model into the evaluation mode, to disable the dropout. This is used to make sure we don't have some overfittings by turning off some neurons during the training. For the pre-processing, we would reverse the string, convert each character into its token index, etc., etc. This is all pretty standard. So we'll run this. Okay, so this is for the important part. It's the testing and execution. We will have 3 examples. One, we would hard code or like show that this equation would give us the correct one, hopefully, and check if it's correct. And then we will ask the user to enter a specific equation, and then just for sanity check we would use a minus sign. Again, we said that we did not learn what this character is, so we should get an error. So let's do that now. Okay, let's enter let's say 200 plus 200. Hopefully it gives us 400. Okay, yes, it did. Again, this is correct, this is correct. Again, and we got an error with the minus sign. So it looks like our model was successful, but what I want to show you is what would happen if we used a shorter training period. Where is the let's say epoch. Okay, instead of 50, let's say, I don't know, let's say 5. Okay, back to the training. Okay, this is the training group. Now we would have only 5 epochs. So what we can expect is the model would make errors even with the plus sign. Not errors, but like not correct or the expected result. Okay, once it's done, evaluation. Now for the test, say 200 plus 300. We expect the correct answer to be 500, but yes, it got 510, which is wrong, mathematically speaking, but it's not very far, especially with only 5 epochs. So that's it. Thank you for watching this video. Please subscribe, and goodbye.